Hello everyone. So in this particular presentation we are going to discuss the coming topics in terms of WDM. So previous topic what I discussed is the principles of WDM. So what you mean by the wavelength division multiplex and what are the different versions with respect to the wavelength division multiplexing. And also we saw about WDM standards where it is consisting CWDM, DWDM, all these particular standards with the different variations or representation in terms of the different values or wavelengths or the all particular concept we discussed about WDM standards. The last two topic what I discussed in the previous session is Mach Zeder interferometer, and I discussed about 2 cross 2 Mach Zeder and also 4 cross 4 also I just mentioned about interferometer. And of course here as per the exam point of view WDM standards is going to be very important, and also this Mach Zeder interferometer is also very important topic. So today's presentation we will see the next coming topics with respect to the isolators, optical isolators and circulators. So I'll just keep on moving. Optical isolators, I'll start with the first. What it means. The optical isolators allows light to pass in only one direction. So the light is which is traveling in one particular direction, that is what optical isolators. So this prevents scattered or reflected light from traveling in the reverse direction. So the light which is not travel in the reverse direction, it will just travel in one particular direction. And what we can do here, can keep backward traveling light can also be done, but with the different versions entering a laser diode, possibly causing instabilities with respect to the optical output. So polarization independent isolators made of 3 miniature optical components. Of course, for this optical isolator we need to have 3 components, like one is set of a birefringent plate with consisting another one birefringent plate which is in the parallel manner where it is going to be placed. And also we have Faraday's rotator with 45 degree. So there is a rotation of a light input which is with a 45-degree angle comparing to the particular axis. There is an 45-degree Faraday rotator to rotate the optical light from one to one way. So what is going to happen, the wavelength which is divided into two different set of ray, like as you can see, when the light which is emerged from the left side, from the input side to the right side, what we can find an O ray and also E ray. So what we are going to happen here, so light is traveling from one direction to the other direction, where the light traveling propagations are going to be different. So that is what the light can pass in one direction, but which is scattered, or the reflected light which is traveling from the left to right. This is what the independent isolators, which is consisting of different versions or many component, what I just mentioned, is birefringent plate and also Faraday rotator. So this diagram, which is indicating polarization independent isolators, as you can see in this particular diagram. And of course the plates whatever I just mentioned, a birefringent plate, this is always made by TiO2, that is the material composition for these particular plates. So next topic is optical isolators. So first of all, what is circulator? Sorry, optical circulator. So optical circulator, it is a non-reciprocal multi-port passive device that directs the light sequentially from port to port in only one directions. So here one example is we are having, that is 3-port example. So port 1, port 2, port 3. So as you can see, so light can enter and it can travel from one port to the other port to the other. So as the example goes like this, an input on port 1 is sent to an out at port 2, an input is coming in the port 2 sent as output at port 3, and the input coming in port 3 sent as output at port 1. So this is what one port to another port transmission can happen with respect to the multi-port passive devices. This example which is mentioned for 3-port example. So why this is used, that is also very important for us, where it can be used and how it can be used. So these devices usually used in optical amplifier, add drop multiplexes, and in dispersion composition modules, where we can use these circulators. So this can have some different passing from one port to the other. This might also going to be very important. Maybe add a drop of multiplexers with respect to the optical fiber. That is also going to be very important point. So coming to the this particular slide, where we can find some tables, but this table which is indicating something typical parameter values of some commercially available something like optical isolators or optical circulators. So what are the commercially parameter value with respect to the optical isolators? So the normally the optical isolators with the wavelength defined, you can see here it is defined in terms of 1310 or 1550 nanometers, the wavelength possibility for optical isolators, and isolations value maximum it can go to till 40 dB, and the insertion loss also less than 0.5 dB that is required, and size, if you look into the diameter into length of optic fiber, should be 6 cross 35 millimeter. So similar manner, we can also have something its particular parameter for optical circulators also. So you can look forward with all these tables. You can keep remember certain values with respect to the isolator and circulator. When the question is asked for optical isolators and circulators, then you can take all these particular points along with the optical circulator and isolators. So next concept is fiber Bragg grating. I can also need to be understand about grating. First of all, the grating is means what? To understand fiber Bragg grating, I just need to understand what is grating. So grating in the sense, it is an important element with respect to the WDM system for combining or separating individual wavelength. We require fiber grating or grating conditions. So either adding, separating of a individual wavelength, I just need to go for the phenomenon is called grating. So how it can be done? So maybe adding or separating of different wavelengths with respect to the any particular optical fiber. So we will perform in terms of grating. So I just need to understand how it need to be developed. So for this purpose, this particular diagram over here, which is giving or which is giving a ideology onto how the grating of a fiber core can be done. So this example or this particular diagram, which is indicating the formation of Bragg grating in a fiber core by means of two intersecting ultraviolet light beams. So as you can see, the two ultraviolet wavelength, different wavelength or same wavelength, can be passed into the in a opposite from the opposite direction with certain angle. They are coming and hitting onto the fiber core. This is what we can see, the fiber, and it consisting of fiber core over here, and light is going to be transmitted over here. That is nothing but interference pattern where the two different wavelengths are coming and hitting. So two ultraviolet beams will be create a permanent interference pattern in a GeO2 doped silica fiber core, or to form a periodic index variation along the axis. So index variation you can find because of these two different wavelength hitting at these particular junctions. So interference pattern will generate that will change the value of the periodic index variation can be observed at the axis of the core. So the incident wavelength, optical wave at lambda naught, will be reflected back in the following grating condition is met. So lambda naught I can find it in terms of 2 n effective with the lambda condition, where the n effective is nothing but averaging weighting of n1 and n2, and the lambda is in terms of grating period, which can also be called as periodicity of index variations. So as you can observe from this, we will have this difference from interference peak to peak. Differences will give the value to with the length of this particular interference pattern will entirely give the pitch of a period. This can also be we can verify with the help of the equation lambda naught to calculate what is the reflected lights over here, and its particular wavelength can be calculated as in terms of lambda naught. So this equation is going to be very important when we were creating the different wavelength in terms of with the help of a grating, either adding or separation of generating of new wavelength. So we can go for the grating phenomenon, and this can be achieved through the help of fiber Bragg grating. So with the help of using this fiber Bragg grating, what we can do? So that is what in this particular slide we are going to understand, that is demultiplexing with the help of fiber Bragg gating. So this also requires some circulators to understand this. So we are going to have the 3-port circulators, optical circulators, along with the fiber Bragg grating unit. So with this combination, we can do the demultiplexing of a wavelength. Nothing but wavelength dropping also we can mention this particular process, either a demultiplexing or the wavelength dropping process. So let us consider we are having for the signal, input signal we are having consisting of 4 wavelength combination wavelength like lambda 1 to lambda 4, which is entering into the circulators from the port 1 region, and it will travel to the port 2. So whenever all the wavelength which is coming at the port 2, the port 2 designed such a way that with the port 2 which is connected to fiber Bragg grating, which was all the wavelength which is coming at port 2 which is coming out. So as the property for optical circulator says, when the input is coming at port 1, which is existed or which is goes out at port 2, that is what we said, all the wavelength lambda 1 to lambda 4 coming at port 1, which need to go out at port 2, but we are connected fiber Bragg grating at the output of the port 2. So fiber Bragg grating is designed such a way that it need to reflect lambda 2 wavelength, one particular wavelength it need to reflect, and remaining it will not disturb. Hence by this condition, lambda 1, lambda 3, lambda 4 which will emerged through the fiber Bragg grating, except lambda 2 it will reflected back at port 2. Nothing but port 2 it will have an input now as lambda 2, which will go and which will dropped out at port 3. So lambda 2, which is a reflection lambda 2 from the port 2 to port 3, which will going to come. So we are dropped one wavelength whenever we passing the light from one to another with the different wavelengths. So one wavelength is dropped, hence this is also wavelength dropping process. So with the help of fiber Bragg grating and also optical circulators, we done a demultiplexing over here. So one more example, similar way with respect to the either the circulators or fiber Bragg grating, we can understand is the multiplexing process. The multiplexing of 4 wavelengths, you can see it in this particular slide. So one need to understand there is N1 FBGs and N1 circulators for combining and separating N wavelengths. So we have first, second, the third conditions of circulators. We can consider one circulator, you can see here one fiber Bragg grating, another fiber Bragg grating we can see here with the different fiber Bragg gratings. So what you can see here, the lambda 1 which is passed into the fiber Bragg grating, so it will come out and it will get in lambda 2 which is emerged over here, which is trying to come out over here but is reflected back. We are designed such a way that it is only this fiber Bragg grating only need to pass lambda 1. It will not allow any other wavelength. So lambda 2 which is reflected back from this port to this port, it need to emerge, but it is reflected back along with this lambda 1. So lambda 1 and lambda 2 which is going to come here. So at this particular fiber Bragg grating such a way that we need to design it, we need to allow lambda 1 and lambda 2. So but it need not to allow any other particular wavelength. So I'll go for another circulator C3. As you can see here, one port at one port, this is again 3-port optical circulators, where lambda 3 coming in one port, it need try to emerge out, but this will not FBG3 will not allow the lambda 3. So it will lambda 3 also come over here along with lambda 1 and lambda 2. So lambda 1, lambda 2, lambda 3 which is there with the light which is coming at port 3 of C3, and then it is emerged into the fiber Bragg grating, the fourth one, where it is designed such a way that it can allow only lambda 1, lambda 2, lambda 3, none other than that. So at C4, as you can see, lambda 4 is the input at port 1, which is trying to emerge out at port 2, but there is a fiber Bragg grating which will not allow lambda 4. It will reflect it back along with the lambda 1, lambda 2, lambda 3 wave. So the new wavelength at another port which is coming out, all four wavelength combined together and it is coming. So multiplexing of a wavelength is observed here with the help of fiber Bragg grating and also optical circulators. So moving on to the next concept, that is the dielectric thin film filters. Dielectric thin film filters is used as an optical band pass filter. This means it allows the particular very narrow wavelength band to pass straight through it and reflect all other. So this is what normally going to be happen, but the basis for this particular device is normally it is a Fabry Perot filter structure. So it allows very narrow wavelength band to pass straight through it and reflect all the wavelengths. So for this particular purpose we need to have something like Fabry Perot interferometer, nothing but it can also be called as etalon. So the devices which is required to perform thin film filters, dielectric thin film filters, we just need to have etalon is required. So how we can see this etalon? As you can see, this is one diagram. This is a Fabry-Perot cavity where it consisting to reflecting mirrors, as you can see, where the light is reflected within this particular Fabry-Perot cavity, which is having the distance or a difference between the two mirrors, reflecting mirrors, as d, as you can see the distance. But over here what is going to happen, that a transmission of light which is going to be into this particular the cavity, or which is generated from this cavity, the transmission T is an ideal etalon condition, ideal etalon in there is no light absorption by the mirrors. With the condition is required, no light is absorbed by these mirrors, because it is need to have certain airy functions. As in terms of transmission T, we can say it is 1 plus 4r by 1 minus r whole square sine square of pi by 2. This is inverse of the this particular value, where r is nothing but reflectivity of the mirror and phi is the round trip phase change of the light beam. Of course, there should be some ignorance with respect to a particular wavelength is required. The periodicity of this particular device with respect to this device is normally called or represented in terms of free spectral range, and this free spectral range should be in terms of lambda square by 2 and d. So as I mentioned, d is the distance between the two fiber mirror reflecting mirrors, and n is the wavelength, n is nothing but a refractive index, and lambda is the wavelength of the light which is passing into this particular thin film filters. So this thin film filters, if I considered with respect to the resonant cavity filters, as in terms of fabric wrote interferometer, there should be consisting a number of dielectric thin film filters or reflecting stacks. If I consider, many wavelengths are passed into this, and it might be reflected back few wavelengths. The mirror surrounding cavity are multiple reflective dielectric thin film layers. The cavity length determines a particular wavelength to pass and reflect all the other flat pass bands with the steep roll off. So we are defined the dielectric thin film filters or something reflectors defined to only particular wavelength range. So as you can see, the steep roll off which is existed for the wavelength value of 0.996 to 0.998, but the major value of the relative wavelength 1, as you can see, this is already normally is going to be passed into the electric thin film filters. So this is what the particular condition when you take up with the multiple dielectric thin film filters together, multi-layer optical thin film filters consisting a different stack, as you can see different stacks over here. So that is consisting of many reflecting filters for the depending upon the input wavelength. So there are few cases, the low insertion, few advantages of this also. Insertion loss is very low. So the high optical return loss, thin film filters with the 50 gigahertz passband are commercially available. So these are the certain advantage with respect to the dielectric thin film filters when you want to do this all these particular operations. So as you observed, if BG fiber Bragg grating, or even in terms of the optical isolators or circulators, we can use this. So this is another pattern to be represented, the array waveguide grating. So this is also called as phased array based devices. So normally this phased array based device is normally done with the help of arrayed waveguide grating. So this is what we taken the diagram of a top view of a typical array waveguide grating and designation of its various operating region. So we defined here in this particular diagram 1, 2, 3, 4, 5, 6, all these different regions. Considering the 2 and 5 are the lens regions, can also be called as the planar star couplers, and the 3 region it is grating array waveguides. The 1 and 6 are defined as input and output slab where the waveguide array which is going to be observed. So what is going to be happen? So the input waveguides enter into the one and into the lens region, to the two region or lens region, or you can also said star coupler or lens region, which is divides the power among the different waveguides in the grating array into the grating array waveguides 3 region. So each grating waveguide has the precise length differences delta L with its neighbors. The light in which the waveguide emerges with the different phase delays delta phi at 4. So different wavelength, the differences, phase delay differences, which will be emerged out at the point number 4 with the help of the equation 2 pi n effective delta L by lambda c, where n effective, the effective refractive index, lambda c is the center wavelength of the defined signal, or considering all this. Next, the second lens at 5, what is going to happen? Refocus of light from the array waveguide into onto the output waveguide array at the point 6. What we can observe, the free spectral range, the with respect to the wavelength delta, which is emerged out with the help of each wavelength is focused into the different output waveguide in this particular region. So the 2, 3 are not retained, which is not taken out, so it will be retained and merged inside lambda 1 to lambda 4, and which is came out. So lambda 1 which is inserted over here with lambda 1 to 4 inserted with respect to the input, and it is emerged with a different way. So phase delay is defined with the respect to the wavelength and which is separated out, and with the help of the phase arrayed based device. So this is arrayed waveguide grating to be defined the separating of all different wavelengths with the help of the grating structure. This slide, which is says FSR example, that is a free spectral range example with respect to the specifies the spectral width that will be separated across the optical waveguide of an AWG, that is nothing but the array waveguide grating. So that is for array waveguide grating, we are defining with the free spectral range. So with the example which is considered over here. So next concept is one more, that is a diffraction grating coupler. This is also one way of separating all the wavelength into the different wavelength, wavelength, all wavelength in one particular incident light, which is separated out and which is passed into different optical amplifiers. So this process is happening in air or nothing but spatially, which is observed. Diffraction grating, which is spatially observed with respect to the wavelength lambda, uh, beams lambda 1 to lambda n consisting in one single beam, which is reflected and hitted onto the reflection grating, where it is reflected because of the different wavelength, which is diffraction grating is different. The lambda is emerged out in the different region, lambda 2 is emerged out in the different angle, lambda n is emerged out in the different angle with respect whenever the hitting and reflecting cases, which is different for the different wavelength. So lambda 1 is whatever separately emerged out, which is pushed into the optical fiber, that is what possibly. So reflection grating are ruled or etched fine parallel lines on a reflective surface. So how this reflection grating looks? So reflection grating looks like this. So as you can see here, it is consisting of parallel different etched fine parallel lines, as you can see, with respect to the reflecting surfaces. The transmission grating which is existed within this reflection grating have periodic index variations. Each wavelength will reflect or refract at the different angle. That's why all the wavelength or the lambda 1 to lambda 4, whichever coming, which is separated out because of this transmission grating also. This is one way representation. This is another way of representation of diffraction grating coupler. So next further concept for today's presentation is the last one, that is active optical components. So there are many active components which can be used with respect to the optical fibers. So first I am just defining is MEMS technology, that is micro electromechanical system. So active component requires some type of external energy, either to perform their functions or to be used over a wider operating range than a passive device, thereby offering a greater application flexibility, that is conditions. So many active component is a kind of micro electrical mechanical system technology, a simple understanding of this MEMS actuation method. So we are having one polysilicon beam placed exactly above of the insulators. So as you increase whenever the voltage, if it is given for the two different plates with the zero, but if you increase the voltage between these two plates, what is going to happen? There is a variation with respect to the different plates. So the polysilicon beam has typically the length and width with the thickness dimension in terms of 80 micrometer or 10 micrometer or 0.0 micrometers can be taken out with respect to the different plates. For the gap also is required between these two initially with the some value in terms of micrometer we can define it. But when the voltage is applied between the silicon ground plane, so the polysilicon beam and the electric force which will pull the beam down so that it will contact to the lower structure. This is what going to be happen when the voltage is applied into particular parallel plates. So there are a few other devices. One is tunable optical filters, can be varied selecting a specific narrow spectral band within a much wider optical band gap. So this is normally is defined as per this particular diagram. You can observe it. The optical filter with have a wavelength range should be in terms of 155 to 1553. So within that range need to be defined. So that is normally required with respect to the WDM optical networks in terms of tunable optical filters as a key. So the diagram which is says the reflection band and steep spectral profiles for a 50 gigahertz fiber Bragg grating. So this is used to define the tunable optical filters. And the next concept is the dynamic gain equalizers. So dynamic gain equalizers, how it need to be. So dynamic gain equalizers is used to reduce the attenuation of the individual wavelength within the spectral band, and these devices can also be called as DCE, that is dynamic channel equalizers, or dynamic spectral equalizers. So DGE, DCE, or DSE, whatever it is. So the names are same, which will equalize the gain profile of an erbium doped fiber amplifier. So it will equalize the gain profiles for EDFA fiber. So that can be happened with respect to the optical wavelength amplitudes from EDFA. So then different wavelengths you can find, so that is equalized with the help of this dynamic gain equalizers. So now the next one active devices is optical add drop multiplexers. This is, I think, already mentioned about add drop multiplexers. Maybe circulators are used to for the develop optical add drop multiplexers, which will insert nothing but in terms of add. Yeah, this optical add drop can also be called as OADM, which will insert or adds or extracts or drops wavelength at a designed point in an optical network. So you can see here, this is the image to represent OADM. So four input, four lights, four signals can be put it on to here. So that can be taken out, that is also possibility. But to the other side, other port, what you can see, all the lights need to be wavelength, need to be passed, need to be added. But one port which is hidden into this particular mirror, and it is get reflected and it is heated and it is just added. So as you can see here, so three whatever light is hitted and it is transmitted. Okay, so this light which is just added with respect to these, but this particular port 2A which is mirrored into and it is passed over here. So instead of this line should come here, this is coming here. Instead of coming this over here, this 3 is coming over here. So this is that optical light which is added. So added, and this is dropped for this region. So add and drop with respect to the optical in terms of wavelength, which can be done with respect to OADM. Thank you.